Okay. So hopefully you are seeing my screen. So can you see my screen?
Yes.
Yeah, okay, great. Uh, okay, so in this warm-up session, my idea is to illustrate what is this area that is called formal methods, but to show this in a very practical way. So I'm not going to use the slides. Actually, my talk is going to be uh, delivered by using this tool, that is the Coq IDE. So Coq is what is called an interactive proof assistant. It has been developed since 1984 by INRIA, so it's not a new tool, it's a mature tool. And it has a number of languages. I would say that it's said that one language of Coq is Galena, which is a functional language quite similar to Haskell, for those of you that know uh, Haskell. Besides Galena, Coq supports a language to develop proofs via tactics, and it also has the so-called tactics language, LTAC, where the user can define new tactics. So this is a very brief introduction to Coq, just to show you the main ideas behind this philosophy of developing reliable software. So if you want to read more about Coq, I have some links. I will share later this file with you. So you have here some links where you can get more information about this too. To illustrate this notion of formal development, I'm going to consider uh, a dictionary, so a mapping between keys and values. And in my uh, example, this abstract data type should support the following operations. So you should be able to clear a dictionary. You should be able to check whether a dictionary is empty. You should be able to retrieve the size of the dictionary, and also inserting new elements and finding elements there. Uh, uh, Before getting into the details, if you have any doubts, please do interrupt me. So don't wait until the end of the session. So please just interrupt me if you want to ask anything, if anything is not clear. And in my example, I'm going to prove that my implementation of the abstract data type dictionary is correct. And I'm going to prove this using theorems. So in this file, I have comments, but I also have commands as well. And now I'm just going to process these commands that are going to import required libraries for my example. As you can see, when I use the tool to process the commands and the commands are processed correctly, you see this green highlight to say that. So if I introduce some typo, you're going to get a syntax uh, error feedback. So to define this notion of dictionary, I first need to have a specification. So when we are talking about formal verification, you need to have a precise definition of the expected behavior. So in this case, in this module called dictionary, I'm going to formalize what is my understanding of a dictionary, and what are the properties that I expect to hold in any valid implementation of a dictionary. So a dictionary, as I said before, is a mapping between keys and values. As a key, I'm to be simple, I will say that my keys are just natural numbers and my values are strings. Since I'm defining an abstract data type, I'm not going to say what is the actual type of a dictionary. So you can implement a dictionary using different data structures. So you can use lists, you can use binary search trees, you can use red-black trees, you can use hashing functions. So you can use different techniques. So in the abstract level, I just say that dictionary has a type, but I don't say what is the actual type of this dictionary. So note that here, I'm not saying that this is a definition. This is a parameter. So in other words, when you are creating an instance, so a data structure that implements this abstract data type, instead of providing parameters, you need to write the actual definitions. So I also need to have the notion of what is an empty dictionary. So an empty dictionary is an element of the dictionary type, but note that, as I said before, the dictionary type is so far abstract. Uh, Regarding the operations, they are also defined here as parameters. So I'm not going to provide their actual implementations. I'm just going to specify the signature of these operations. So clear is a function that provided a dictionary, it returns another dictionary. Uh, is empty is a function that yields a Boolean value. Size is a function that yields a natural number. Insert is a function that provided a key, a value, and a dictionary. It's going to produce a new dictionary. And find is another function that provided a key in the dictionary. It's going to produce as output an option val. This option, for those of you that are familiar with Haskell, is like the maybe in Haskell. So this return can be some value, so some 3, some 4, or it can be none. So none encodes the notion that there is no value mapped to this key in the provided dictionary. So far, I have just the signature. So how do we encode? How do we formally specify the expected behavior of these functions? We do this by defining axioms, so by defining properties that must hold on any valid implementation of a dictionary. So I have here a number of axioms. For instance, clear empty is an axiom that says that for any dictionary, if I, after clearing a dictionary, if I check whether it is empty, the obtained result should be true. So in this way, I'm kind of formalizing the expected behavior of the clear function. And I have a number of axioms here. So for instance, clear size, it states that after clearing a dictionary, the size of this empty dictionary should be equal to 0. Uh, Another one states that if a dictionary is empty, this is true if and only if D is equal to the empty dictionary. So the only dictionary that is said to be empty is the empty one. Recall that the empty dictionary is this parameter of this definition. Another axiom states that uh, if a dictionary is empty, this is true if and only if its size is equal to 0. So as you can see, most of these axioms are quite intuitive, are quite basic, so they are not hard to understand. Uh, Another definition states, axiom states that for any dictionary, if it is empty, if I try to find any key in this empty dictionary, I will get as a result none, because I don't have anything in the dictionary, so I cannot find any key in it. Uh, Another property that is expected is that if I insert a key and a value in a dictionary, and after doing this, I try to find the value mapped to this key, so the same key that has just been inserted, the output of this function application should be equal to the value I have just inserted. Another axiom states that uh, if I try to find a key in a dictionary and I cannot find a value mapped to this key, sorry, I can find a value mapped to this key, so the result is different from none. In other words, there is a value mapped to key to k in the dictionary D. So if this is true, when I insert a value mapped to the same key, this is not going to change the size of the dictionary. In other words, I'm encoding here that if you try to insert a value mapped to a key that is already in the dictionary, the behavior of this insertion should be encoded by just updating the mapping, but not increasing the size of the dictionary. So in this specification, I cannot have duplicate keys. So the keys are unique. And the last axiom, it states the other side, that is, if I try to find a key in a dictionary and I cannot find it, if I insert some value mapped to this key, in this case, this will increase the size of the dictionary. So the size of the modified dictionary should be equal to the size of the previous dictionary plus 1. Okay? So this ends my specification. So when I execute this command and dictionary, you can see in this console that the module type dictionary has been defined. So now I have a formal specification of what is the expected behavior of a dictionary. Again, if you have any questions, please just interrupt me or say anything in the chat. So now I'm going to use Coq to create an implementation.
Gustavo,
So
I believe that we
yes,
have a question
yes, please.
uh, from Joabe Jesus. Can you create contradictions using axiomatizations in Coq?
Yes, you can. The short
What
answer, yes.
would be the impact on your formal development if you do not have caution in defining such axioms?
Uh, the short answer is you can't prove anything. So you can prove wrong statements. Uh, but in this case, this use of axiom is a bit different because I'm defining just an abstract notion. When I want to create an implementation of this abstract notion, I am obliged to prove all stated axioms. So if I state a wrong axiom in this case, when creating the implementation, I will not be able to prove the axiom, and a Coq does not allow finishing the creation of the implementation. A slightly different situation is that when you are using axioms not in the context of abstract data types, but you are creating some theory and you axiomatize something. So in this case, I can write here an example. So axiom test that states, for instance, that 1 is equal to 0. This is an absolute, of course. Note that in this case, the tool highlights this definition with this orange-yellow background uh, to, let's say, warn me that I'm defining something that I'm assuming to be true, but I'm not going to prove that it's true. And there is a specific command in Coq that when you prove some statement, you can ask the tool to list all axioms that have been used to prove that statement. Have I answered the question?
Yes,
Okay. Okay, great. Uh, so let's continue. So now I'm going to create the concrete implementation. So in this case, I'm going to use a binary search tree. So I'm saying that I'm creating a dictionary implementation based on binary search trees. So the first thing I need to do is define the binary search tree type. And I do this using this inductive definition. So I have here a polymorphic BST. So this binary search tree is a binary search tree of any valid type in Coq. And I have two constructors for creating such an element. I have B now, nil, to create an empty binary search tree. And I have the constructor B node that provided an element of X and two binary search trees, so the left one and the right one. This will produce a new binary search tree. I have here some pieces, some code to ask Coq to infer automatically the type of X, so I don't need to provide them explicitly. So now, key is and val is just as before, but note that now the dictionary, this element is not anymore a parameter, but it's a definition here. So when I create an instance, everything that has been defined as a parameter in the specification needs to become a definition. And furthermore, every axiom written in the specification should become a theorem proved in the implementation. So in this case, I'm going to say that my implementation of dictionary will rely on the notion of binary search trees, and the element of each node is going to be a pair relating a key and a value. And the empty dictionary is basically the application of the B-nil constructor. And now what I need to do is I need to define an implementation for all functions defined in my abstract specification. So the function clear, I just say that provided any dictionary, the output is just B nil. So the output is going to be always is going to always be the empty dictionary. The function is empty is defined using partner matching. So if D is a dictionary constructed with B nil, I return true, which means that the dictionary is empty. Otherwise, I return false. Size is defined using recursion. So differently from the previous definitions, where I was using the definition keyword, now I use the fixed point keyword. And I say that if D is a dictionary created using the constructor BNIL, I just return 0. Otherwise, I will return 1 plus the size of the left subtree and the size of the right subtree. Insertion is performed as usual. As usual, I mean, if you were implementing a binary search tree in your favorite programming language. but here in a functional style. So if the dictionary is empty, I just create a node with the pair I want to insert, and this subtree is going to be a leaf. In other words, the left and the right children are empty, are null. Otherwise, so if the dictionary is not empty, the first thing I do is I check whether the first element of the pair, remember that pair relates keys and values, so I check whether the first element of the pair is equal to the key I provided for the insertion function. If this is the case, as I said before, I don't create a new node. I just update the node related to this key. So if this is the case, my return will keep the left and right subtrees unmodified, but this node will be updated with the value provided to the function. Well, if the key I'm trying to insert is not the first element of this pair, of the root of the tree, I check whether this key is less or greater than the key of the root. If it's less, I'm going to perform a recursion to the left subtree, so the result will keep the right subtree unchanged, the pair of the root unchanged, but the left subtree of the root is going to be updated by this recursive call. And in the second case, so if the key is greater than the key of the root, I recurse to the right subtree. And at some point, I will find or a node with the same key, and I will update, or I will reach a leaf, an empty leaf, and in this case, I will create a new node at this empty leaf. Find, which is the last operation, is implemented quite similar to the insertion one. The only difference is that I'm trying to find an element and not modify the tree. So after providing a body to all functions, to all operations of my abstract data type, now, as I said before, I need to prove all stated axioms. And just relating again to Joab's question, if you have stated a contradiction, you would not be able to prove that axiom here. And this would prevent you from finishing this definition. And now, so I use this theorem keyword and this keyword proof to say to Coq that now I'm entering in proof mode. So note that when I process a theorem command, it appears on this part of the tool. What is the goal? What is the proposition I need to prove? And when I process the command proof, now Coq is able to recognize the application of tactics. So these special commands that will manipulate this proof goal in order to prove that it holds. So I'm going to briefly explain some tactics. As expected, Coq has a huge number of tactics. I'm just going to cover some of them and just some applications of some of them. So the intros tactic performs what is known as universal instantiation. So instead of proving a universally quantified predicate, I try to prove this proposition for an arbitrary dictionary. So this is what is performed by the intros tactic. The simplification tactic simplifies my proof goal. So when I perform this tactic, my proof goal is rewritten as I want to prove that true is equal to true. And every time uh, that I have a proof goal where the left hand side is equal to the right hand side, I can use the tactic reflexivity. And these finishes this proof goal. Since this was the single proof goal of my theorem, I have also finished the proof of the theorem, and I can use the command QED to state that now this property has been proved to hold on my implementation of dictionary using binary search trees. But if I try to just illustrate, if I try to cheat, and okay, I'm finished. I don't have anything else to prove. The Coq IDE is say, that's not, you're not behaving properly. There are other properties that you need to prove. And I'm not going to allow you to finish your definition until you prove that all expected properties hold. So I need to prove all the previously stated axioms. Uh, the theorem clear size is proved in the same way. I think I should say that my proof scripts here are quite verbose because I'm trying to show you the step by step of the proof goal manipulation. But if I were writing these proofs, I could have written with in a more concise way. So let's go to a more complicated uh, property theorem, this one. So as before, I'm going to perform universal instantiation. So I want to prove this proposition for an arbitrary dictionary. And note that here I have a if and only if. So as you may remember, an if and only if is defined as a conjunction of the implications from both sides. So I can use this tactic called unfold to unfold some definition. So I'm saying here, please unfold the definition of the if and only if command. After doing that, uh, I know that I need to prove two implications. And now I use the split command to say, okay, I'm going to work on each implication per time. Because if I need to prove a conjunction of two clauses, uh, the conjunction is true if and only if all clauses, in this case, the two clauses are true. So I'm going to split my goal into two sub-goals, and I'm going to address each one separately. So this minus sign here says to Coq that, okay, now I'm focusing on the first sub-goal. So here I'm using intros again, but with in a different context. Note that I don't have a universal quantification here, but I have an implication. So as you may remember, uh, the implication truth table, if the antecedent is false, it doesn't matter whether the consequence is true or not, because the whole clause is going to be true. As you know, false implies in anything. So what I'm doing here is that I'm trying to prove the consequence of the implication, assuming that the antecedent is true. Because as I said before, is if the antecedent is not true, I don't need to worry because the implication is going to be trivially true. So I need to prove, let's say, the hard case. So if the assume that the antecedent is true, I need to show evidence that the consequence is also true. Now I'm going to address this proof goal, performing a proof by case analysis. So the destruct command says to Coq that create cases that will uh, encode the possible ways of creating a dictionary. So when I do this, it generates two sub-goals. The first one, the dictionary is empty, and in the second one, the dictionary is not empty. Uh, so I use this other symbol here to say I want to focus now on the first sub-goal of the first sub-goal, and I unfold the definition of the empty dictionary and I reach an inequality that is trivially true, and I can finish the proof by using reflexivity. In this case, uh, I'm trying to prove that this non-empty dictionary is equal to the empty dictionary. So it's clear that my proof goal is not true. So in this case, I need to look into my assumptions, into my hypotheses. So it turns that this hypothesis is a contradiction. So if I simplify H, so if I apply simplification in H, I get that I'm assuming that false is equal to true. And as I said before, if the antecedent is false, so if I have a contradiction in my proof context, the proof is done. And I can use this tactic called discriminate to finish this proof goal. Well, the other way around of the implication that I need to prove to show that I have an if and only if is quite similar to the first branch. So I'm just going to skip this. One thing that I'm not going to illustrate during this very brief talk is that Coq has a number of uh, uh, higher level tactics that allow you to automate part of your proofs. Uh, so I have here another theorem, empty size. Some commands are already
Gustavo,
know. Yes, please.
we have a question
Yes, please.
from Williams. These statics are like necessary and sufficient conditions to the proof?
Uh, I would say that they are necessary, but you could have written, well, it depends on the theorem, but it may be true that you can use different tactics in different sequences of applications that will prove that something is true in a different way. So, for instance, if I go back here, uh, if I have written just reflexivity, in this situation, that's enough. So as you can see, the proof script with reflexivity and the proof script with these three tactics, both of them proves the goal, but in slightly different ways. So I would not say that when you have a proof that these tactics are sufficient. Well, I would say that you have an instance of a proof, but you may have other ways of proving the same theorem. Was that the question?
I believe that's answered. Thanks.
Okay. You're welcome. Okay, so let's see what we have new on this theorem. So intros split, moving antecedents of implications to the proof context. Here we have a new tactic called rewrite. So I can use previously proven results to perform rewriting of terms. So in this proof goal, I have in my context, in this proof, I have in my context that the dictionary D is empty. But I have proved before that if a dictionary is empty, the dictionary is equal to the empty dictionary. So I can say, please rewrite the H hypothesis using this theorem and performing the rewriting from left to right. So try to match in H the left-hand side of the theorem and substitute it by the right-hand side of the theorem. So after performing this task, my hypothesis is going to change to D is equal to the empty dictionary. And now I can perform another rewriting by rewriting D in my proof goal, considering H. So where I have D in my proof goal, I will substitute by the right-hand side of the equality in H. And now I have as a proof goal that the size of the empty dictionary is equal to 0. And after simplification, I get that 0 is equal to 0. And I can finish this proof by reflexivity. The second proof goal can be proved using tactics that we have already explained before. So I will skip them. This other theorem does not have anything new in terms of tactics, so I will just skip it as well. Skip the explanation. I cannot skip the proof, otherwise, as I have shown you, a Coq will not allow me to conclude the definition of this data structure. So here we have something different. We need to prove this new theorem, and in this case, I need to perform this proof by induction. So Coq has a tactic named induction, and as you would expect, when I perform this tactic, it will create a base case and another proof goal for the inductive step. In the base case, I need to prove this statement, this goal, assuming that my dictionary is empty. So the binary search tree is empty. So I need to prove that after inserting this pair in the empty dictionary, in the empty tree, if I try to find the value mapped to K, this will be the value that I have just inserted. If I perform simplification, I get this maybe scaring proof goal, which is basically the unfolding of find. And note that I have this condition, if K is equal to K. Well, I don't know what is the value of K, but K is always equal to K. So Coq has a number of already proven statements, and I can rely on them. So in this case, I say, okay, rewrite my proof goal using the theorem that states something about the reflexivity of the equality of natural numbers. So when I do this, Coq is going to manipulate this proof goal and say, okay, this is true. And if the condition is true, what is left is what is inside the then clause. And note that everything here is equal to this. So this term is simplified to just sum v, and I get a trivial equality proof. In this other branch, which is inductive step, note that Coq has already created for me the induction hypothesis. In this case, I have two induction hypotheses, one related to the left subtree and another one related to the right subtree. Here, I'm going to use destruct again to perform case analysis, but differently from before, instead of performing case analysis on a value, I'm going to perform case analysis on an expression. So when I perform this destruct command, I'm saying, okay, this is an expression. Moreover, this is a Boolean expression. And as a Boolean expression, this expression can have only two possible values. It can be false or it can be true. So please consider both cases for me. And on each case, please create a hypothesis called H, which will encode uh, the situation you are considering on this proof branch. So in the first sub-goal, I'm trying to prove this statement, but assuming that that expression is true. In other words, what I have here is I'm trying to prove this, assuming that uh, the key I'm inserting in the tree is equal to the key of the root of the subtree I am. So if you remember the definition, in this situation, the behavior of insertion is updating the value mapped to this key. So if I perform simplification, I get this. Note that again, I have that k is equal to k, which is trivially true. And I can get rid of this using rewrite. And I reach again that trivial goal that sum v is equal to sum v. In this case is a bit more complicated because I know that I'm assuming that the key is not equal to the key of the root of the subtree I'm in. So according to the definition of a binary search tree, when I'm in this situation, I need to recurse either to the left subtree or to the right subtree. So I perform another destruction command uh, with this other expression. So please perform proof case-based analysis. Consider whether k is less than the key of the root of the subtree I'm in. In the other case, k is going to be greater than the root. So if it's lower than, I can perform some simplifications and use these hypotheses here to rewrite this complicated if then else clause. So I have here that this condition is false. So I can rewrite this here. So I will just say false here. So if I say false here, I'm left with the with the else clause. And the else clause, the condition of the else clause matches the hypothesis H prime. So I can rewrite here as well. And since this is true, I will be left with the then clause of the if clause. And it turns out that my proof goal now is equal to my induction hypothesis. And I can just say, please apply the induction hypothesis, and I'm done here. And the other branch is similar. So I would like to emphasize. Yes, please.
We have a question.
Yes, please.
I'm waiting you finish the explanation of this theorem before I ask it. The question from Joabi again. He asks about the Isabelle community is migrating to use a more legible proof language called Isar. And he asks if Coq does have such a similar feature, such a more legible program proof language.
As far as I'm aware, no. Okay, so there might be some initiative to create something like Isar, but I don't know. Okay.
Thanks, Gustavo.
You're welcome. So one thing that's important to emphasize here is that I said in the very beginning that Coq is a proof assistant. It's typically different from what is called a theorem prover. Because when you say that a tool is a proof assistant, the underlying message is that it's not going to finish the proof for you. It is just going to assist you. So the responsibility on developing the proof script relies on the user. So you can see that I needed to write these comments. It's different from other tools, for instance, Isabelle, some cases, where you can use some decision procedures or some heuristics to, okay, try to prove this for me automatically. So this is not the main idea behind Coq. So in Coq, the proof scripts need to be written by someone. One thing that you can do is you can use that language I mentioned before called LTAC to encode decision procedures that will automatically prove some propositions that share a common structure. I'm going to illustrate a decision procedure just now, right? Uh, so I have here some more theorems. I don't have time to go into the details, but the tactics are just going to be repetition of the tactics we have seen so far. So nothing new here. However, in this case, I will jump to this point of the proof. In this branch, at this step, I need to prove this statement, which says that the successor of the size of D1 plus size of plus 1 plus size of D2 is equal to the successor of these. For us humans, this is true. Well, we know that the add command is commutative. But if I say to Coq, okay, this is true, please help me, just finish this. Reflexivity, it's going to complain. Because actually the tool is not smart. You need to instruct the tool how to prove everything. So there is in Coq a decision procedure based on the Prisburger arithmetic that has, let's say, an algorithm for proving a subset of propositions involving sums, subtractions, and things like that. And this decision procedure is called omega. So I can say here, please try to apply the decision procedure omega, and it can finish this proof call. But again, this omega tactic uh, was defined by someone who needed to encode the decision procedure I mentioned before. Okay, to finish, one thing that we can also do in Coq is extract actual code. So, oops, I didn't highlight a very important thing. When I finish this last theorem here, I have proven all previously stated axioms, and now I can finish the definition of my concrete data structure. So if I run this end command, it says, okay, I trust you. Dictionary based on BST is defined. And furthermore, it obeys to all properties stated in the formal specification. So if this is a first talk you are listening about formal methods, that's the main difference when you are developing software in a traditional way. In a traditional way, you have a specification, you write your program, and you test it, and you test it again. But typically, you don't have a guarantee that your implementation will always behave as expected. It behaves as expected considering the cases you tested. But here it's substantially different. I have just proven that any valid instance of a dictionary implemented as a binary search tree, considering the functions I have shown you before, they will always meet the properties stated in the abstract data type. So this is a much stronger result. And typically, in some cases, for instance, when you are developing critical systems, you expect this stronger uh, evidence on the correctness of your code. And the last but not least thing I would like to mention is that you can, for instance, extract Haskell code from this formal specification and implementation of dictionaries. So I can use these commands. And when I say extraction, it generates a bunch of files that will have the Haskell code for everything I showed you. It's important to say that the theorems are not translated to Haskell. What is translated to Haskell is the data types, the functions, so the behavior of your code, but not the proof that your code is correct. The proof was created to provide you some evidence that your implementation is, let's say, reliable. Okay, so with this, I conclude my walkthrough the Coq Proof Assistant. It's a quite big universe. I have just talked a bit about it. So I hope you enjoyed. And if you have any other questions, I would be really happy to answer them.
Thanks, Gustavo, for a great introduction to Coq Proof Assistant. I would like to open the questions from the audience. If someone has some question regarding Gustavo's talk, please open your microphone and camera and go ahead. I believe that's a new question on the chat. How automatic are the proof tasks in Coq? How much guidance do you need to do?
Right. So you have in Coq what is called tactics. So like these I have shown you. Some of them are quite simple. Let's say, for instance, destruct, you need to say the expression, how it's going to be considered. Some other tactics are a bit more, let's say, intelligent. So for instance, there is a tactic called contradiction that will search your proof context for a contradiction. So you don't need to say, as I have written, discriminate H. You can just write contradiction. And in Coq, you have what is called tacticals. So there's tactic and there is tacticals. And tacticals are meta tactics, so higher level tactics. So you can create combination of tactics, and using that language LTAC, you can create even more uh, sophisticated, complex decision procedures. So I would say that in the end, you need to create the decision procedures, but if you create them, you can prove some statements in a very automatic way. To give a concrete example, I had a student uh, that was formalized in process algebras in Coq, uh, and he has formalized the notion of traces. So he has a relation that holds if a sequence of events is a trace of a given process. And to prove this relation, he has created a decision procedure he called solve trace relation. And to prove any theorem using an expression in terms of this relation, we just need to invoke this decision procedure. So for the user of the theory, it seems quite automatic, but when we were constructing the theory, we needed to encode this decision procedure.
Okay, thanks for the answer. More questions? I have a question. Oh,
Yes,
there's
please.
another one here. It's possible to develop critical systems without the use of COC or other proof assistant?
Yes, there are many different formal methods. Some of them are general, so for many domains. Some of them address specific domains. So when you are reasoning about concurrent systems, when you are reasoning about timed systems, so the answer is there are many formal methods. You need to pick the ones that will help you to get the evidence of correctness you expect. So proof assistant is not the only technique in formal methods. During the ETMF, we are going to have a tutorial on model checking, which can be seen as a complementary technique for proving properties. And in ETMF, we are also going to have another tutorial, another lecture with me, when I'm going to show you many different formal languages and formal tools. So CSP, timed automata, and DuPal, probabilistic behaviors. So we have, the COC is not the only way.
Thanks, Gustavo. There's another question. It's a bit long in the chat. Are you able to read it?
Yes. So André said that he's very new to this topic, so probably an amateur question, no problem at all. In the context of IoT devices, but not exactly critical systems, let's say a smart lock, it certainly would be bad if it were to malfunction. But in my opinion, not as bad as a train or airplane system malfunction. Would this tool be useful, or are these less abstract, or are there less abstract tools used for digital security? Uh, I'm not very familiar with formal methods applications to digital security, but I know that there are some tools that are applicable in domains that are not necessarily critical. I'm going to mention one tool. There is a tool. Oops, what was the? Yes, I had just forgotten the name, but I remember. There is a tool that has been developed in the University College of London, and now it's maintained inside Facebook, called Infer. And as far as I know, in the actual development of Facebook Mobile, when you are committing code, this formal tool is used to analyze, for instance, the Java code you have written, and if the tool suspects that you may have a problem in your code, it doesn't allow you to finish your commit. So you could say that Facebook Mobile, uh, well, may not be a critical system. Well, if it goes off, certainly a lot of people will get crazy. But it's not a, let's say, a typical critical system. But a failure in Facebook, for sure, would have a financial impact that's not trivial. So you may use formal methods not only on developing critical systems. I would say that you need to use formal methods uh, every time you need to have a higher confidence on the reliability of the software you are developing.
Okay, thanks, Gustavo. Another question is about it's possible to use COC to prove properties of programs with mutability?
Uh, I'm not sure about your meaning of mutability. Are you talking about uh, programs implementations that are not functional, so using an imperative language? I will suppose that yes. So you are asking whether we can use Coq to prove imperative programs. If this is a proper question, the answer is also yes. So there is a framework called VST, so the Verified Software Toolchain, where you can write C code. So it's not functional, it's not Haskell, it's actual C code. And this tool is capable of translating your C code into Coq, and then you can prove properties like absence of race conditions, absence of memory violation using Coq. So it's not restricted to implementations in functional languages. You're welcome.
Thanks. Well, more questions?
Okay,
I believe that we could thank Gustavo for this excellent lecture about Coq Proof Assistant, and finish this for the second warm-up section for SBMF 2020. And I hope to see everyone on the next week on eTMF and the SBMF properly.
Thank you very much. I would like just to highlight that if you know some friend, colleague, or student that would like to know more about this subject, please invite him or her to join us next week. I hope we're going to have an excellent event. And there is another question, but I will answer in the Slack since we are already run out of time. Okay. So thank you very much and see you next week.